श्रीचक्र वरदाचार्यं शुद्धसत्व गुरुत्तमं श्रीनिधिं राघवं वन्दे ह्यपार करुणाकरं. Namaskaram to all. It's my great pleasure to introduce a great scientist, Dr. Tapan Kumar Nayak, an Indian who is working in CERN, Switzerland. And welcome, sir. Welcome to our channel.
Namaskar.
It gives me immense pleasure. And this CERN is definitely a place of cultural significance for us Bharatiyans, because we have got an idol of Lord Nataraja at CERN. Because if you observe the form of the dancing Shiva Nataraja, he has got the musical instrument drum in his right hand and fire in his left hand. If you observe closely, that musical instrument and fire will be held at the same levels, which shows that in CERN they are researching about microparticles, thereby researching about the creation of universe. There you can see the energy created is exactly equal to the energy destroyed. So the drum sound, which signifies creation, the fire which signifies destruction, are at the same level, which shows the law of conservation of energy. Energy created is equal to energy destroyed. Not only that, they found that the particle movement it has got a rhythmic fashion. Even Lord Nataraja, you can see, he is dancing. Dance always has a rhythm. So that kind of a cultural significance we have got. Now it's a great pleasure, great opportunity that Dr. Tapan Kumar Nayak sir will share some insights, some very useful insights for our channel people regarding CERN and other things. Over to you, sir.
Yeah, okay. Very nice. Namaskar. Very nice to meet you and also talk to you today. It's really great pleasure to meet Maharajji, and also really very nice to talk to him. And at CERN we are looking for basically fundamental physics. This is a place for nuclear science or high energy physics, and we are looking for fundamental science, how matter got created, what are the fundamental understanding of the forces in nature, what are the understanding of the constituents of matter basically. And we more or less correlate with how the Big Bang started. It may not be exactly directly one to one, but we try to understand how the Big Bang has started. So when Big Bang started, let's start from there, time t equal to 0. When time t equal to 0, it was a point like infinitesimal, very small point, like very high energetic point, which started and expanded extremely quickly, and then within few tenths of microseconds, many things happened, in fact. So you have the fundamental. So to understand this, two things I will tell you. One is the fundamental particles which we have, then fundamental forces. Fundamental particles are, you all know, it starts from matter to molecules to atoms. Inside the atoms you have the nucleus, which was discovered in 1911 by Rutherford. Then the electrons scattered around the nucleus, and then inside the nucleus you have protons and neutrons. Protons are positively charged particles, neutrons are neutrals. For many years, till 1950s, 60s, we all thought that protons are the most fundamental particles. And then 1960s, we have a great experiment in Stanford. It's a Stanford Linear Accelerator Laboratory Center, SLAC, where we did an experiment called deep inelastic scattering experiment, similar to Rutherford experiment, but in a high energy. Then we found the proton, neutron, they are not fundamental. Inside that, we have quarks. So quarks are very small, very small. Proton, neutron is about 10 to the minus 13 centimeter. Quarks are about 10 to the minus 18 centimeter, called attometer. Attometer. So these quarks are very interesting characters, in fact. So the quarks, their charges are fractional charges. Like electron has a charge of -1, positron +1. Quarks are fractional charges. And quarks are even another different property which doesn't exist regularly. You have Coulomb force between the electron electrical field, positive charge, negative charge. If positive negatives are together, they attract. Positive negatives, when they pull them apart, they repel. The force goes down. But in quarks, actually the opposite. The force increases when the distance increases. So very interesting characteristics. But before that, let me tell you. So we have up to the quarks. So we want to see the quark structure. Quarks in fact existed in the beginning of the universe. So we want to see a quark thing. So that's why you need very high energy. It's a de Broglie wavelength, lambda equal to h by p.
Okay.
So if you want to look at a higher energy, you have to if you want to look at a very small particles, you have to give very high energy,
Okay.
extremely high energy. So for quarks, to see quarks, you need something like a Large Hadron Collider of CERN, where you can look at the quarks.
Okay.
Otherwise, you cannot see the quark.
Okay.
Then the other thing is the fundamental forces. One is gravity, electricity, magnetism. Third one is called weak force. It's like beta decay. It's like an example of the weak force.
Okay.
The fourth one is called a strong force. The strong force is one which is responsible for keeping quarks inside the proton neutron,
Okay.
or proton neutron inside the nucleus.
Okay.
That's really strongly packed. Inside the
Okay.
nucleus are protons.
Okay.
How so many positively charged particles stay together?
Yes.
That is strong force. So in the beginning of the universe, there is a grand unification, we think, and where all four forces are united like one.
Okay.
Then slowly they got decomposed,
Okay.
decoupled, and within a microsecond, it was only strong force. It was only quarks which existed.
Okay.
All the four forces existed, but they are like separated now.
Okay.
But these quarks became, within a microsecond, the quarks realized, oh, I am a quark. I cannot stay by isolated. Listen,
Okay.
I have to combine to become a proton or neutron or
Okay.
another particle.
Okay.
So then, after a microsecond or few microseconds, there is no quarks anymore. It becomes proton neutrons. They confined within the
Okay.
proton neutron pion,
Okay.
and we have not seen quarks in isolation ever.
Okay.
Okay, that's the interesting part. So beginning of the universe, within a microsecond, we are looking for something quark. We call it quark-gluon plasma.
Okay.
QGP.
Okay.
So the quarks, they interact through gluons, and yeah, that interaction we see. How is the interaction? That's called QGP, quark-gluon plasma. So our goal in my experiment, especially here in Alice experiment, is looking for quark-gluon plasma which existed within a microsecond of the Big Bang. The properties of the quark-gluon plasma is that extremely high temperature and extremely high density.
Okay.
The temperature is nowhere we can see the in nature. The temperature which existed that time is extremely high.
Oh.
And then it becomes something like, we call it a hadron, like a proton neutron. After that, we have not seen anything like that. So what we do at CERN, we collide particles at extremely high energy at the speed of light. So we collide protons, proton, that is the main, most of the time we collide proton.
Okay.
We also collide ions, like the lead ions. When the lead ions are like much bigger than protons. When they collide, in the collision, you have lot of energy.
Yes.
Which Maharaj said already, you have energy. That energy which is performed here, that energy equal to produces particles, E equal to mc square.
Okay.
That energy produces thousands of particles. In our experiment, we measure the particles and try to reconstruct how these particles are created in the beginning, or how the little bang, we call it a little bang instead of a big bang, how that was created.
A replica.
So, replica. Now, you can ask me whether you have seen the quark-gluon plasma or not. Yes, we have seen the quark-gluon plasma because there is a theoretical model which says if you are above this temperature, above this density, you have a quark-gluon plasma. Our temperature we see, which is more than 200,000 times the core of the sun. The sun temperature is very high, right? The core of the sun is extremely high temperature, 20 million degree or something. We see temperature 200,000 times more than that core of the sun.
Okay.
So at that temperature, we think there is a possibility that we have quark-gluon plasma. We see a quark-gluon plasma structure. Then when we measure these particles which are coming out, if they are coming from quark-gluon plasma, then we can explain them.
Okay.
If they are not coming from quark-gluon plasma, we cannot explain what we see.
Okay.
We see a lot of observations. From all our observations, we see now we have created quark-gluon plasma, but it's very small time. It stays only 10 to the minus 20 second, 22 second, 10 to the minus 22 seconds or something like that.
Okay.
Extremely high temperature, extremely high density.
Okay.
So that's the temperature density, very similar to beginning of the universe which I have created in a small scale. We only now are studying what is the properties of that matter.
Okay.
What kind of matter it is made of? It is a liquid, it is a gas, or what is its viscosity, what is the electrical properties, what is its thermodynamic characteristics, specific heat, all that, conductivity, all that thing we are studying in much more detail.
We read during our school days physical properties,
Yes.
chemical properties.
Yes, all those we are now studying in detail.
Okay.
So for next 10 years we will be studying that
Oh.
in fact. So quarks in fact when they are inside, they are completely inside the proton, they are completely free. Inside the proton they move freely. But if we try to pull out one quark, you can't pull out. You put lot of energy.
Okay.
So what happens, you have to, let's say 2 quark, you give energy, so you pull them out, then energy is so much that the string itself breaks. When
Oh.
it breaks, you have another energy. That energy creates one quark and another anti-quark.
Ah.
They form another particle.
Okay.
So you cannot see quarks freely. They are always inside protons and neutrons.
Okay.
Only when you collide using these heavy ions like
Okay.
lead ion,
Okay.
when you collide, you compress them and you heat them up. For
Okay.
a fraction of a second, they just lose their identity. Proton
Okay.
loses their identity. The boundaries break,
Okay.
and you have a quark-gluon plasma.
Okay.
For a small time, particles are coming out, and very high energy particles are coming out if there is a quark-gluon plasma.
Okay.
Then again they combine to form proton, neutron, pion, kaon, thousands of particles,
Oh.
including, in the beginning if the energy is very high, we see quarks which are very light quarks, or we'll see very heavy quarks.
Okay.
There are 6 different types of quarks we see. Now our effort is to see very heavy quark and how they behave when they go through this plasma. It's very high temperature, high density plasma. When they go through, how they behave, what happens, what is the density of the plasma, we measure through that.
Oh.
So that's really very fundamental. At CERN, this is one of the experiment. All the experiments are looking for these things.
Okay.
The other two other experiments called Atlas and CMS,
Okay.
they are looking for something commonly known as God particle.
Ah.
So God particle, that's the Higgs boson,
Yes.
which is responsible for giving mass to other particles.
Yes.
They got Nobel Prize, Higgs got Nobel Prize in 2013.
Okay.
Discovery was 2012.
Oh.
Then there is a fourth experiment called LHC-B. In the beginning of the universe, when they started, the matter and antimatter,
Okay.
they are all same. Matter created 100 gram, antimatter also created 100 gram. Matter created 10, antimatter also 10.
Okay.
They are in the same because of the conservation.
Yes.
But now you see matter only. There is no
Yes.
antimatter.
Yes.
There is no anti of Maharaj. So right, we see only matter.
Yes.
Right. See, there is an antimatter very tiny that will kill everybody.
Yes.
That will destroy everything.
Ah.
Right. That destruction will happen.
Yes. Yes.
So what happened in the beginning of the universe that we see matter only, there is no antimatter. We all are looking for that, but the fourth experiment called LHC-B, they are specially looking for that kind of physics.
Oh.
Specially. The field where I am called quark-gluon plasma, that is just 50 years old. 1974-75 that theory came, and then we started doing experiment.
Okay.
So we are now preparing for 50-year celebration of this
Great.
quark-gluon plasma.
And we wish you all the best for
Thank you
your
so much.
50
Thank
years,
you.
and we
Yeah.
pray to the lotus feet of Bhagavan for more and more success in your field as well. And I have to thank a lot for enlightening our audience as well.
Oh, thank you.
Because it was a really enlightening lecture from you. And for 1 minute, I wish to add one thing.
Yeah.
When you were explaining about those forces,
Yeah.
you said there was one strong force, and before creation, the other 3 forces were not identifiable as separate entities from that strong force.
No, one force we call grand unification.
Okay.
Grand unified. All 4 forces are together.
Okay.
Strong force is one of the 4 forces.
One of the 4 forces.
So gravity, electricity, magnetism, weak and strong.
Weak and strong.
So all 4. But the separation time was different.
Okay.
The strong force was the last one to separate.
Okay. So they were all unified,
Yeah, and unified.
and they could not be identified as separate before creation.
So now we are trying to understand, for example, science-wise, the 3 forces could be understood very well in a model called standard model.
Okay.
Other than gravity,
Okay.
these 3 forces we understand very well. So now a lot of work is going on, but not at CERN, other places,
Okay.
to understand gravity itself, gravitational force.
Okay.
So, but the other 3 forces we understand.
Okay.
So we think that beginning when the time started t equal to 0, all 4 forces are 1. Then I have a timeline how they separate.
Okay.
But I can send it to you.
Why did I come to that point is, in Chandogya Upanishad,
Yeah.
we have got one verse.
Okay.
Sadeva Somya idam agra asit ekameva dvitiyam. In the initial stage, there was only one entity, Paramatma, Super Soul, Bhagavan, and he was all encompassing. Everything was within him in subtle form, which could not be identified as separate
Yeah.
entities.
Yes.
They were separate
Yes.
entities, but they could not be identified
Yeah.
as separate
Yeah.
entities. They were in subtle form, micro
Yeah.
form with
Yeah.
him.
Yeah.
As the creation took place, God made a sankalpa, a divine
Yeah.
will.
Yeah.
Bahusyam prajayayeti. Let me
Okay.
become many.
Okay.
Let me become identifiable by many names and
Yeah.
forms.
Yeah.
Saying so, he converted the micro or subtle aspects
Yeah.
which constitute his own body
Yeah.
into macro or gross forms. Thereby, creation came into existence. This has been said in Chandogya Upanishad, and great acharyas like Ramanuja call this as Brahma Parinamavadam, the evolution of God Himself. God Himself evolves, but the inner God doesn't change, of course. But the all the matter and souls which constitute the body of God, they change. They undergo a transformation and they undergo differentiation, thereby leading to creation of this universe. Likewise, you also said initially the all the matter, they were all in the form of the quark particles, which are not identifiable externally. They are subtle,
Yeah.
micro,
Yeah.
and then from that matter evolved. The same theory our acharyas also say in Brahma Parinamavadam, the evolution of Brahman. They
Yeah.
say everything was in a subtle form, micro form,
Yeah.
and then Bhagavan, out of his sankalpam, changed everything into macro form. So I suppose that micro form could be that quark particle,
Yeah.
and macro form could be this external,
And
whatever we
yeah,
say,
what do you
molecule
see?
and everything.
What do you see?
So
Yeah.
this 10-minute interaction with you gave me a lot of insights. How much our acharyas, how much
Yeah.
our rishis they were able to
Right.
convey.
Right.
So this CERN visit is not a mere scientific visit; it's also a spiritual visit.
Yeah.
Thanks
No.
to you, sir.
Yeah. Thank you so much. Thank you for
So we
your
have to thank
insight.
actually Bhagavad Ramanuja. 1,000 years back, he was
Yeah.
able to explain this
Yeah.
Brahma Parinamavadam.
Right. 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 Yeah.
So it
Our
was very
Upanishads were
enlightening.
very rich
Yes.
in this scientific background also. Yeah. A lot of mentions. Thank
So
you.
and
Thank you.
thank you
Namaste.
very much.
Namaste.
Namaste, and on behalf of all our viewers, I thank you. On behalf of all
Yeah.
of you, you have got a great scientist once again, Dr. Tapan Kumar Nayak, and people like you. You carry the heritage of our country, our nation's pride, working in CERN in this place. So thanks
Namaskar.
to you, sir.
Thank you so
Thank
much.
you.
Thank you.
Namaskar.
Thank you. Namaskar.